In this lecture, we're going to look at the hardware that we use on layer 1, 2, and 3 of the OSI model. In our networks, we have a ton of different equipment that has very specific roles, and it does that one thing very well, but only that one thing. So on layer 1, we have repeaters, and we have talked about those before. Even though they're not very commonly used, there are still some of them left in the field. Basically, they receive a signal, they amplify that signal, and then they send it out another direction. And we use these when we have really long stretches of copper. The farther and farther away we get from the central, the attenuation drops. That correlates with the speed. So every so often, we have a repeater. They receive the signal, amplify it, and send it out to the next central. That does the same, and the next one, and the next one. We have also briefly talked about hubs. They were very common 15, 20 years ago. By now, they should mostly have been phased out, but I'm pretty sure we still use them in a lot of places. They are basically repeaters with more than 2 ports. With hubs, all traffic is sent out to all ports. We have no confidentiality, we have no integrity, it's half duplex, and it is in no way secure. Everything is on the same collision domain. The next step then was moving to bridges, and bridges are layer 2 devices. And we used those early on when we were using hubs to make sure that the collision domains we had were not getting too big, not too congested, so every so often we would put in a bridge, separating them into different collision domains. In the early 2000s, I had an internet cafe in California, and we had, I think, 35 or 40 computers. At that point, switches were really expensive, so we had 2 hubs, and then we had a bridge in between them. The 20 computers on the left side of the room were on one hub, the 20 computers on the right side were on another hub, and then those 2 hubs were connected with a bridge. And the image over here on the right really is a representation of that. Computers on the left, computers on the right, a bridge in the middle to divide the collision domains. So the 2 computers on the top left and top right would never see each other's traffic unless a workstation from the left needs to talk to one on the right. Bridges are a step forward, but they're still not secure. Which then brings us to switches, and switches are just bridges with more than 2 ports. And since every single port on a switch is its own collision domain, that fixes the biggest problem with CSMA, which were collisions. Every single port is its own collision domain, meaning there are no collisions. A standard switch can range from somewhere between 4 and 500 ports. And yes, technically, some switches are layer 3 switches, which means they can route IP addresses. But for the exam, just assume the switches uses the MAC address of their client to direct their traffic, and understand that some switches can also use IPs. When we made the move from hubs to switches, of course, we don't have the issues with collisions, but on top of that, we also don't broadcast all the traffic out all the ports, which inherently is more secure. On top of that, we also need to follow best practices for security on our switches. That means that any port that is not used, we shut down, and we shut the ports down to make sure that either malicious or non-malicious traffic doesn't happen. It can just be Bob bringing his laptop from home so he can game at work, or he's tired of not having Wi-Fi coverage in the area he's in. He brings in an access point, plugs it into an open port from someone who left the company. Now, if we have not shut that port down on the switch, then Bob and his devices will have access to whatever VLANs that employee was in. Then we put ports in specific VLANs. We make sure that all the ports are in the VLANs they need to be and none that they shouldn't be. That means if our HR department and our accounting department needs access to different things, well then we put them in their own VLAN, and that's just a virtual LAN. And even if someone from HR is plugged into one port and the next one is accounting, they can't see each other because they're logically segmented with the VLANs. We will cover VLANs more in about 2 minutes. We also use the MAC sticky command. That automatically adds the MAC addresses that it sees on that port to the port configuration, and we don't have to hardcode the appropriate MAC addresses for that specific port, which would just take a tremendous amount of work. So on the switch port configuration, we would use the command macsticky2 or macsticky3. That means that the first 2 or 3 MAC addresses that is seen on that port is added to the configuration automatically. And once those 2 or 3 MAC addresses are on the configuration, anything else that's plugged into that port will not work. And the reason we use MACSTICY 2 or 3 is because in most cases, we would have an IP phone and we would have a desktop. That's 2 MAC addresses at least. If we use MACSTICY 2, Bob has an IP phone and a desktop. If I go over to the patch panel in the wall, unplug the cable going to Bob's phone, plug my own in, I can't get access because the MACSTICY is at maximum. And yes, MAC addresses are insanely easy to spoof. It's just another layer in our layer defense. Now, if instead of me trying to plug my desktop into Bob's port, it's just Bob getting a new phone. The old one died, IT comes out with a new one, they plug it in, it doesn't work. Here again, we need to go in on the port and clear the MACSTICY. And no, don't be lazy and just raise the MACSTICY count. And with the MACSTICY, what happens whenever you plug the next device in that exceeds the MACSTICY count? Well, that depends on your configuration. It can either completely shut the port down or just give us a warning. If it shuts the port down, well then, obviously, we need to figure out how it happened, and then we need to clear the conflict and re-enable MACSTICY so Bob can keep working. And then finally, we have trunk ports and VLAN pruning. We have touched on this before. A trunk port is a port we have between 2 switches. And here, we need to make sure that we enable VLAN pruning. Now, let's look a little more at VLANs. This is where we logically segment the LANs we have, we split accounting from HR, and we do the VLAN pruning between the switches. And all that really means is we only send the VLAN traffic across between the 2 bridges for the VLANs that they share. So if you look over here on the image on the right, we have 2 switches and we have 4 VLANs. VLAN 1, 2, 3, and 23. And yes, I know, we wouldn't normally use VLAN 1 for something like this. But for this example, bear with me. Let's assume each switch is in a separate building. That means the top building, we have HR, accounting, payroll, and then we use voice over IP. In the bottom building, we only have payroll. Since accounting, HR, and voice over IP is never used in the bottom building, we can prune those VLANs from the trunk ports. The only traffic we need to transport between the 2 switches is the payroll VLAN, VLAN 3. If we think back to the MACSTICY, if we look at the 2 top users, the one on the right only has the PC, no phone. Here we can do MACSTICY 1. The one on the left has a phone and a PC. Well, then we do MACSTICY 2. Now for the phones, VLAN 23, we need to make sure that traffic has priority since it is real-time or near real-time, whereas the PC is not as important. So any traffic from VLAN 23 has higher priority than VLAN 1, 2, and 3. And each VLAN is its own broadcast domain that is partitioned and isolated on layer 2. And to make that work, we use VLAN tagging. Every single packet on the network is tagged with the VLAN that it belongs to. Since it is tagged, we know which logical broadcast domain it belongs to, and we don't need to have a separate switch for HR and accounting and payroll and phones. We just logically segment every VLAN, which for us, of course, makes it cheaper, and it also makes it much easier. It's more secure, and we can much easier do proper traffic management. On enterprise-level switches, it's also normal to have dedicated ports that have much higher speeds than the regular ports, and those are used for switch-to-switch connectivity. Let's say we have a normal 48-port switch. All the 48 ports are 1 gig ports. Then it's very normal for that switch to also have 4, 10, 40, or 100 gig ports, which makes sense. Those are the ones that transport all the data between the switches. If we just use the regular 1 gig ports, we would have congestions. This way, the trunk ports don't become bottlenecks. But if, for whatever reason, our switch doesn't have the higher speed ports or they're broken, well then we can just use a regular access point, but we need to make it into a trunk port. So the port on the switch that the PC on the top left is plugged into would be in VLAN 1, accounting, and VLAN 23, voice over IP, where the switch port the top right PC is plugged into would only be on VLAN 1. Now let's finish out VLANs by looking at VXLANs, or Virtual Extensible Local Area Networks. And this is something that was made and is mainly used for cloud computing, and not really for small organizations or even small cloud providers. This is Google or AWS. They can easily have tens of thousands of customers that need multiple VLANs each. Since regular VLANs are limited to 4094, this obviously caused a problem. So they made VXLANs. Now they can have 16 million VLANs with a 24-bit VLAN ID. And then they added a couple of things for the use case, since cloud providers really aren't local anymore. They added MAC in UDP encapsulation so they can extend the layer 2 segment across locations, and VXLAN is really an encapsulation protocol that we can run on our existing layer 3 infrastructure, which also makes sense, right? Once we hit layer 3, that means that traffic is routable, then I, as a company, can have my infrastructure in multiple AVS data centers, and I'm not limited to one location because unlike normal VLANs, this is not only layer 2. We have added layer 3, making it routable. And since I just said routable, let's talk about routers. With switches, they could have up to as many as 500 ports, which makes sense. They are what we connect all our end devices to. Routers have an entirely different function, and because of that different function, they have very few ports. They would normally be either in our data center in our organization or at the DMARC from the ISP. If we talk about the one you have at your house, then most often it's one box that combines a router, a switch, and a wireless access point. And since routers are layer 3 devices, that means that they forward all traffic based on the source IP and ports. Routers is what we use to connect our local area network to the wide area network. And in most cases, with a very few exceptions, the inside IPs on the routers are private addresses. The outside IPs have to be public addresses. Remember, private IP addresses gets dropped at the router border when it exits to the WAN. Private addresses are only used internally. Every single router keeps a routing table, and that basically tells it traffic going to this destination should be sent this way. There are multiple ways that a router can get updates to its routing table. We can configure a static route. A static route is something we configure in the router saying all traffic going to this destination should be sent that way. We can tell it all traffic to this subnet should be sent out that port. We would also have a default route, and that is us saying all non-local traffic, we send that out that port. That would most often be to our internet service provider. Our local router doesn't need to have a huge routing table to figure out how to send stuff to you. We just tell it if it is a public address, send it out this interface to the internet service provider. And the service provider's router will then make the decision on how to best get our traffic to the destination. Next up, we have dynamic routes. And those are routes that our router learned from another router. And they learn those routes through routing protocols. That can be OSPF, EIGRP, BGP, ISIS, or whatever else we use. All those protocols use metrics to determine what is the best path to this destination, and they can either do that with the shortest path, where they look at how many devices from here to there. So if there's one path where there are 6 routers before you get to the destination, and another path that has 8, well then distance vector routing protocols will send all the traffic out the path that only has 6 routers regardless of how fast that path is. Whereas a link state routing protocol would look at the bandwidth of that path and choose the fastest path, regardless if it is 6 or 8 routers on that path. We have briefly talked about how routers have 2 planes of operations, a control plane and a forwarding plane. One plane makes all the decisions, and the other one transmits the data. The control plane is where we keep all our routing tables, where we choose which route should we send this data and which interface should we send it out of. This is where we would have the static and dynamic routes, and in that control plane, we have all those routes stored in our routing information base, RIB. It then strips all the non-essential directives from the RIB to build a forwarding information base, which is what the forwarding plane uses to send the traffic. In the forwarding plane, the router forwards all the data between the incoming and outgoing interface connections. And it does that using the network type from the packet header, and just like FTP, the control plane is the brains. It figures out where to send it, and the forwarding plane sends the data. And with that, we are done with this lecture. I will see you in the next one.